Let us continue with aspects related to the tangential force in DEM simulations. These forces are meant to model friction between particles. So if we have a granular material and now we look at the contact between two particles, we not only have a normal force, but due to the surface asperities, small scale roughness, we have surface frictional forces. And those frictional forces are characterized by the friction coefficient mu. So let us consider now a simple situation where we have again two particles. We load them with a normal force Fn here, same as before. The normal force at the contact here can be modeled with, for example, a linear spring dashpot model. Let us now assume that we apply a lateral shear force and prevent the rolling of the particles. Particles are not allowed to roll. Also, let us assume that we are not moving essentially, we are very slowly moving only in the worst case. So the time derivative of the momentum mv is 0, meaning that these two forces globally must be the same. And if we now look at an individual particle, we also see that this shear force that we apply must be compensated with the exactly same tangential force here at the contact. So what will happen now if we increase this lateral shear force, right? So this tangential force here, Ft, which is shown here on this axis, will steadily increase from 0, right? Because these two forces must be balanced. The force will increase further until we reach the Coulomb limit. The Coulomb limit is given by the friction coefficient, which is a material property of the two particles. It depends on the pair of the materials that we use, and the normal force. This normal force is, in our case, constant, and we know that force. If we now increase this shear force beyond this Coulomb limit, what happens is that this tangential force can no longer increase. So it will plateau at this level of the Coulomb limit. And this is very important to know, and is also reflected by this equation here. What will happen, of course, if we do that? The particle will accelerate in this direction because the shear force is larger than this tangential force, and this condition no longer is valid. There are now two important things to mention. First, this Fn must be here the contact normal force, but not the total normal force. For example, if we have cohesion, there is an additional normal force acting in this direction, and it's then important to realize that this Coulomb limit needs to be calculated only based on the contact normal force. So you have to be careful in case of cohesion. That is typically taken into account by the DEM simulator. The second, more important thing is that for any practical situation, we don't know this shear force because, as you have seen on the previous slide, we have a multi-body situation, multiple grains interact, and there is no clear shear force that we could then use in this expression for the tangential force. So the calculation of the tangential force is a little bit more involved, and we need so-called tangential force models or tangential force closures. And this is illustrated here. Let us assume now that these two particles make an oblique collision, so they are not colliding heads-on, but they have a shear component. What will happen then is that these stars here that demarcate the contact between the two particles, the initial contact point, this point will translate tangentially in addition to the normal translation. This is now important because this tangential overlap which is different from the normal overlap, can be calculated by considering the translational speed of the two particles and an eventual rotation of the two particles. So we know this tangential overlap. This is very important. The tangential direction can also be identified based on this tangential overlap, and now we have the right tools at hand to calculate the tangential force. First of all, of course, the tangential force is acting in this tangential direction. This t hat here is nothing else as a unit vector pointing in the tangential direction that can be identified from the particle collision point and the speed of the particles as well as the rotation rate. Again, we can use Newton's third law, actio et reactio, and this should be clear already to you that the force on particle I must be negative force on particle J, and of course this is also the case for the tangential force components. So to again sum up and stress this important point, we introduce here this tangential overlap in addition to the normal overlap. This tangential overlap is, as I said before already, the contact points deformation history in the tangential direction. This is important for you because in many DEM tools we speak of a so-called history model, and this refers to this tangential overlap. So now how can we benefit from this information? Well, we can start with a very simple sliding friction model that uses the information of this tangential overlap. Specifically, this very simple model just says, well, if there is a positive tangential speed, this delta t dot is nothing else as the time derivative of the tangential overlap, we apply a tangential force in the opposite direction. And if the tangential overlap speed is in the other direction, we do it like this. This is not a really useful tangential force model, since you see we don't have this typical increase of the force when we approach very small velocities. Another point is that we have here a discontinuity in the predicted force, and this is numerically sometimes a problem. Also imagine that the particles form a static pile that is hardly moving, just not really moving, right? Then this delta t dot is very small, and then this essentially pile would start to melt and flow because of this assumption that this tangential force is only proportional to this tangential velocity. Thus, we need an improved model. And what we have done here is that we have introduced a damping coefficient in the tangential direction, Ct. And now we do something more physical. We take the minimum of a force that is calculated from this tangential overlap speed delta t dot and the Coulomb limit. If we would look at this in a graphical way, we would see something like this. We have here this linear relation between the tangential velocity and the tangential force. And of course, we enforce the Coulomb limit. Again, this model is suboptimal because it is not suitable for slow flows. Imagine again that we have very slowly moving particles. The tangential overlap is also very slowly changing, and hence also this tangential force is always close to zero, meaning that we cannot model a static pile. The advantage of this model is, compared to the model that you will see on the next slide, is that we don't need to memorize the tangential overlap. We just need the tangential overlap time derivative, this delta t dot, which is the tangential velocity. And this velocity can be calculated without knowing this tangential overlap, simply because it's calculated from the velocities of the particles and their rotational speed. Let us now come to a model that's very often employed in DEM simulations, which is a linear spring dashpot with sliding friction tangential force model. You see here that we have added a spring in the tangential direction here. If we would write down the equation for this model, it would look like this. This is this spring force, which is in parallel to the damping force, so it needs to be added up, and it's bounded by the Coulomb limit. This is this frictional slider here. And this model has now all the physics inside to model realistic tangential forces in granular packings. The reason for that is that if the particles are slowly moving, they can build up a tangential overlap delta t, and this force is now proportional to this. And even in case the tangential velocity is very small, so particles are hardly moving, there can be a substantial stick force here. Of course, we can also impose the frictional limit, the Coulomb limit in this model, and that's it. The drawback of this model is that it requires the knowledge of the tangential overlap, so we need to save this information because the tangential overlap cannot be calculated from the velocities alone, but it must be integrated in time. This is why this model is often called the history variant of the tangential force models. That's it already. See you next time.